So I know Sitabra for a long time, and it's great to see him and catch up, to see what's going on. So my name is Srinivas, and so I, like I said, I work at BT department. So today I'm going to talk about our ongoing work on computing with oscillatory networks or computing with rhythms. So my lab is called the Computational Neuroscience Lab, and our big goal is to build a whole brain model. It's a simplified model, not like the Blue Brain project, which is super complicated and to take millions of dollars, hundreds of millions of dollars, right, to build it in such great detail, but probably it's not necessary and not even affordable. So we want to build a simplified model with all the main components of the mammalian brain or human brain. Then develop applications in both medicine, that is clinical neuroscience and engineering. That's a big goal. I still have 8 years to go before I retire, and hopefully my group will make it by that time. So to that end, we define this kind of a model. It's a visualize this kind of a model called a mesobrain. It's at mesoscopic level, but again, people are all over the place when you define what is a mesoscopic level, exactly what scale. So so this will have all these components. You have the ascending sensory pathways, vision, touch, and sound, and descending motor pathways, musculoskeletal, oculomotor, and speech. And then you have decision making regions of the prefrontal in between, and then you have three major loops, the detours, cerebellum, basal ganglia, and hippocampus. If you can construct this, if you can have even a reasonable first order theory of each of these structures, you are done. I mean, rest is detail. I think it will be a very powerful model, and we have been working on different pieces of this big picture. So we have put in almost like 20 years into basal ganglia model. So that's biology, right? I mean, I'm sure anybody in experimental biology will know the kind of complexity that you're dealing with. For me, it was a big culture shock. In fact, when I moved from electrical engineering in PhD at UT Austin to neuroscience division in Baylor, so my mentor introduced me to the HOD or chairman of the department, saying that, oh, he's Professor so and so, he works on acetylcholine receptor. He's been working on it for 20 years. I said, what the hell? I mean, what is there to work on a protein for 20 years? But that's biology. I was ignorant. I didn't know that things are so complicated in biology. So anyway, so we put in almost 20 years into basal ganglia modeling. We have a unified model of how basal ganglia works. Many different aspects of basal ganglia function can be integrated and explained using a single model. We published a book on that. Then we have done some work on hippocampus and spatial navigation. Hippocampus is called the GPS of the brain. So we have some kind of unified model of how this you can develop all these representations of spatial cells in this model. Some work on vision and eye movements, motor function, hand, gait, all that bunch of decision making stuff. So the pieces are growing, and so I have my lab is divided into a bunch of teams. Each team works on one problem, or there's one well defined goal. So they have basal ganglia team and stroke team and spatial navigation team, things like that. Even my lab, we put all these stickers right to various aisles, so that when a visitor comes, you just see a bunch of computers. Doesn't make any sense. I mean, you don't see any machines, right? You don't see, there's no EEG or anything. So we just put these stickers and arrows so that people can relate to what's going on. Right? This is the hippocampus alley. This is the basal ganglia alley. This is oscillator alley or whatever. So today I'm going to talk about our work on oscillators. So I mean, this is a comp neuro workshop. So I don't need to tell you about neurons and spikes and all. You all know about it. So but just for sake of completeness, if you record from a single neuron, you will see the sharp voltage fluctuations called action potentials, right? And this is just a hypothetical picture. So the big question here is, what is the information present in this waveform consisting of action potentials? So as you know, that there are two theories about it. One is called the spike code, where people think that since the spike shape itself doesn't vary much, it's more or less standard, atomic almost. So the information is present only in the spike time. So you can represent the series of spikes as a series of delta functions. So that's called the spike code. So then if you look at the other camp that says that you don't even have to worry about exact spike times, right? It's all just there in the average frequency of the spikes. So or the rate of spikes. So that's called the rate code. So based on these two approaches, you also have appropriate neuronal models. You have the spiking neuron models and you have the rate coded neuron models. So rate coded neuron models are very popular in the AI side of the of the situation, and you have the sigma ordered neuron or the ReLU neuron, and right, which are very popular in AI model deep networks. And if you want dynamics and memory and things like that, you have the long short term memory neuron, LSTM unit. With this you can construct large networks with lots of hidden layers, and now the current trends are like trillions of parameters and with big computing farms, and you see the power of AI in every day. I don't need to explain that to you. And if you go to spiking neuron models, you have again lots of options, starting with the simplest leaky integrated fire neuron, which you might have studied in the conference or even before. And then you have the Ezekiewicz's brilliant neuron model with 2 variables, where just simply by tweaking the parameters you can get a wide variety of firing patterns. And then you have the famous Hodgkin-Huxley model, which is pretty much one of the first computation models of, like in computational neuroscience, and more detailed biophysical, large biophysical neuron models, where even for a single neuron you can have large number of parameters. I mean, I have seen models where you have 500 equations for a single neuron, have 500 compartments. So, that is pretty standard, right. So, you see a wide range in terms of complexity when you go to more bio-inspired or neurally inspired neuron models. So, this is an integrated fire neuron, Ezekiewicz 2 variable model and Hodgkin-Huxley model, and you can have detailed biophysical model where you have represent the cables as transmission lines and break it up into small units. You have ladder circuits representing cables and things like that. Now, you have a very important modeling question, a modeling dilemma, which is on one hand you have super simple sigmoidal neurons which are super artificial, but they are very powerful because the whole AI world is built on top of that. On the other hand, you have this very detailed single cell models, where for single cell you have 500 and compartments. What is the sweet spot? Because this is very biological, but too complicated to handle, not very practical. This is super simple, but extremely powerful in terms of practical applications. What is that sweet spot where it is sufficiently biologically inspired, or some kind of biological plausibility is there, at the same time it is computationally tractable? What is that sweet spot? I mean, it depends on exactly what is your question, what is your objective. You can move that that needle both left or right. So, here one analogy you can make is you do not need that kind of a very detailed models, depends on the question, because perhaps single neuron is not the right level at which you construct networks. So, for example, if you look at the problem of designing an aircraft wing in aeronautical engineering, you do not describe the fluid as a bunch of molecules colliding. You invoke this abstraction called fluid and use Navier-Stokes equation. Just because it is abstract does not mean it is flaky or right, it is very rigorous. The equations are very rigorous and very powerful. So, you can design the wing without getting to single molecule level. So, similarly in case of brain also, you can operate at a level where the fundamental unit is not a single neuron, but a collection of neurons, a neural ensemble, and then the collective state of that entire ensemble will be your state variable, right. That makes it it makes it very convenient. You do not have to go all the way to static neuron models like sigmoid neurons and all that. You can still have dynamics, right. I will show you how you can do that. So, people have given a term for this. So, if you instead of recording from single neuron and measuring spikes, you can record from a whole neighborhood of neurons and neural ensemble, and and then in a kind of low pass filter that you get a smooth signal called the local field potential. So, let us take that as take this as a fundamental unit of computation in the brain, and this as a state variable for that, a local field potential. And if you want to model that, you can model it as simply oscillations, because oscillations are very popular in even traditional neuroscience. Even long before Hodgkin-Huxley model, way back in the 20s, Hans Berger has recorded from the scalp and developed this EEG, electroencephalogram. So, since then the idea of brain waves has become quite popular, because people have recorded these signals and looked at various bands in these signals and given names to them. So, you have delta, theta, alpha, beta and so on, and there are a lot of functions are attributed to each of these bands, right. And I am not going to get into all those details, because there is no good theory of oscillations in the brain. So, you can say gamma does this and theta does this, but I mean it is all lots of empirical stuff without any grand theory of why these oscillations do what they are doing. So, that is what we would like to get to. I mean, it is a long haul, but I mean that is the whole idea. So, because there are no oscillations in deep networks, absolutely nothing, right. Whereas the oscillations in comp neuron models are all spikes, they are not really oscillations. So, there is a problem, there is a missing piece somewhere in between. How do you fill that piece? That is the whole objective of this talk. Now, so Gyuri Bazaki is a big name in the field of brain oscillations. So, in a science paper, he and his co-author Dragon, they are saying synchronous activity of oscillating network is now viewed as the critical middle ground. That is the missing piece, that is in between these two extremes, right, middle ground linking single neuron activity to behavior. So, let us try to explore this middle space, right, and then see if you can have a elegant theoretical framework by which you can produce oscillations, study oscillations, and also do very interesting stuff like learning how to drive a car and and whatever the practical problems of AI. So, can we do that? The oscillators are getting
When you see an oscillator,
it's one neuron, right, one unit. It's one unit, two variables.
right, but realistically,
Okay. What do we call neural ensemble? Like a few thousand, 10,000 neurons. That's the scale.
and especially how
Fraction of a millimeter, even smaller actually. Because once I begin the network, that's an abstract network. I'm not going to commit to a specific scale, but roughly it is that scale. So, oscillations are important, becoming important again. There is a revival of interest in oscillations even in the electronic circuits. For this reason, using oscillations for computing, because apparently von Neumann, the father of modern computing, way back in the 50s, he proposed that, or he foresaw that. It's energetically more efficient to use oscillations to compute and represent binary information. So, in digital electronics now, you represent binary information as levels of digital voltage. High voltage is 1 and low voltage is 0, something like that. So, whereas von Neumann thought that if you have oscillators, coupled oscillators, and the phase differences can represent binary information. So, 0 could be 0 and pi could be 1 or something like that, and even has a patent on that. But somehow for some reason the hardware of computing hardware did not evolve on those lines. We somehow switched to digital electronics, and we have now this very energy intensive kind of a hardware. Right? That is why when you have a computing farm these days for AI, you need to have huge circulatory arrangements to cool the system and so on, whereas brain does not need that. I mean, even if you are doing very intense thinking, your vessels will take care of all that. So, there is a recent review paper by Saba and Porod which talks about how you can compute with oscillators, but it is still a field in a very nascent stage. Oscillators are not new in comp neuro. You have models like Wilson-Cowan and Fujii-Naguma, which is actually a two variable reduced version of Hodgkin-Huxley model, and Maurice Lecar and Van der Pol is like a workhorse of nonlinear oscillators. People have used it left and right for everything in engineering, in biology, for beating hearts, to oscillations in mechanical engineering, and everywhere people have used it. So, when it comes to neuroscience, people have used this kind of two variable limit cycle oscillator models. Sometimes they represent single action potential, sometimes they represent ensemble activity like in neural mass models, right. People have interpreted them differently, different ways. Here we will look at them as representing an ensemble of neurons without exactly committing to how many neurons. It's an ensemble like 1,000, 10,000, half a million, whatever. So now let us get to this. So, this kind of oscillator models, these are limit cycle oscillator models. I suppose most of you know what a limit cycle oscillator is. So, compared to a simple harmonic oscillator, which you might have studied in your high school, right, where there is a periodic solution and this is equations and it goes round and round. Right here, if you change the initial condition, so if your initial condition is close to the origin, it will make a small loop. If it is far from the origin, it makes a bigger loop, like a pendulum, for example. If you start with a small initial amplitude, it will make a small swing. If you start with a large initial amplitude, it will make a large swing. The amplitude is dependent on initial condition. There is no fixed amplitude intrinsically. Frequency is intrinsic, but amplitude is not intrinsic. That is a simple harmonic oscillator. Whereas a limit cycle oscillator is different. No matter where you started in the state space, it will always go to that particular loop and keeps going round and round. The action potential is that kind of an oscillator. It is not a SHM, it is a limit cycle oscillator. So with this kind of a preamble, well, I just want to say that we have taken this particular very popular limit cycle oscillator. In fact, the simplest kind of limit cycle oscillator perhaps is the Hopf oscillator. People give it different names. There is Andronov Hopf oscillator or Stewart Landau oscillator, many different names, small variations of the equations. But let us take this equation. So, in fact, if you this looks slightly complicated with cubic nonlinearity on the right side and so on. But if you change it to polar coordinates, x and y convert to r and theta, you get a very simple equation pair. This is r dynamics, this is theta dynamics. R dynamics, you can see very easily that if r is less than 1, right, the right side is positive, so r increases. If r is greater than 1, right side is negative, so r decreases. So, r tends to go to 1. Okay, this equation, that is what it is telling you. and theta, what does it do? It simply is equal to theta dot is equal to 1. So, it's fixed angular velocity of 1. So, it goes round and round. So, what that means is, if you start, no matter where you start in the state space, it will always go to a radius of 1 and keeps going round and round. So, it keeps going round and round the unit circle. That is a limit cycle oscillator. So, very simple one. But the nice thing about Hopf oscillator, which is crucial to our theory, is that you can express it in complex domain. So, the same equations, if you write combine x and y as x plus iy into and z equal to x plus iy, equations become this. You can easily show again how this and the previous equations are the same, right. And so, now with that as a basic unit, now we will set out to construct networks. They are very convenient. I will make some interesting assumptions, and so with that we can construct very general networks. The goal of this whole exercise is to build general trainable oscillator networks, because what happens, and I do not know if you are familiar with any oscillator networks, oscillator network models used in biology. People use them for example, to model locomotor rhythms or any swimming activity of some of the creatures like lamprey and fish and all that. But very often these networks are hard coded. They are designed to perform certain kind of oscillatory movements or oscillatory activity. Whereas a brain is also, it is very strange, if you are modeling a oscillatory movement like saying Tata, right, then you use oscillator networks. But if you are punching or making a reaching movement, you use some other model. That is rubbish, because the same oscillatory brain is producing both apparently oscillatory movement and a non-oscillatory movement like this. So, how do you have a general trainable oscillatory network model that can produce all sorts of outputs, right, whether oscillatory or non-oscillatory? So, that is a whole problem. So, the goal now is start with the Hopf oscillator as a basic unit and construct networks which can be trainable, and literally rework the entire neural network theory in oscillator terms. Is it possible to do that? What does it mean? Oscillatory Hopfield networks, oscillatory autoencoders, oscillatory deep neural networks, oscillatory self-organizing maps, oscillatory convolutional networks, etc., right. We have done all this over the last few years. So, that is what I will talk about. So, let us start with Hopf oscillator. First of all, an oscillator is expected to have some kind of a resonance property, and Hopf oscillator indeed has that. And that is worked out well in this reference scheme and large, right. So, basically x axis is the difference. So, you take a Hopf oscillator of intrinsic frequency some omega, right, omega naught, and then apply a external sinusoidal oscillation as right of frequency omega. Then look at the difference between the two, omega naught minus omega, that is the x axis. So, when difference is 0, you got highest response, right, in the oscillator. But as you deviate from that, there is a bigger difference. Beyond a point, the oscillator does not follow the input frequency, and then you see like there is no stable phase or stable frequency, and that is what is shown in this flanks. So, this central peak is narrow in a narrow band, the oscillator follows the input oscillation. So, now that is just something as a property of a single, there is a huge bifurcation analysis done on a single Hopf oscillator with a sinusoidal input. I mean the paper, Kim and Lodge talks about that, I am skipping all that. Now, let us start looking at networks. So, start with two oscillators, how do you couple them? So, if you couple two oscillators, so then let us see what happens. You can couple back and forth like W12 and W21.
Wait, what is the dip? Can you explain this?
This one. Yeah. So, what happens is, let us say this is the frequency of the oscillator is omega naught, and input is like some I naught into e power I omega t, right. So, and then you vary, the difference is omega naught minus omega, that is your capital omega. Okay. So, now you vary the difference between these two frequencies. When there is no difference, then there is resonant effect in your highest response and amplitude. This is the amplitude of the oscillator. So, mod z. As you increase the deviation, the amplitude goes down. By that, what we mean is, if the frequency here is omega, it is close to omega naught, the oscillator actually oscillates at omega, not omega naught. So, because it is following the input faithfully with some phase difference, that is also worked out. But after some point, it fails to follow the input frequency. There is a mixture of the two frequencies and there is a drift of frequency. That is what is shown in this gray band. The loss coupling between the input, not respond to the input, right? Is that okay? So, already there is a problem when you have single oscillator with a driven by an oscillation, a sinusoidal input, complex sinusoidal input. Already you see kind of seeds of misbehavior. but there is only a small band within which there is a stable response. Now, if you take two oscillators and couple them, both have same frequency, and then there is a coupling strength W1 to W21. Now, let us see what happens.
So, in the coupling strength for this for neuron, what is the coupling strength? I mean, if Z1, Z2 are two neurons or
Z1, Z2, you have two neurons, two oscillators.
So, what is the coupling strength between two?
I'll tell you. So, I take consider two cases. In the first case, W12 and W2 are both positive, symmetric and positive. Other case, again symmetric but negative. Okay. When it is positive, see what's happening. The two oscillators start oscillating in sync. There is a zero phase difference, and that phase difference is shown here. Starts from some initial phase difference and goes to 0. When the coupling strength is negative, the phase difference goes to pi. Right. It does not matter exact value of the coupling strength, only the sign matters.
So, this could be random, any value.
Which one?
Yeah.
You can show it in algebraically. Right. So, it only depends on the sign, not on the exact value. So, the thing is, so what is the moral of the story? When you have two oscillators and couple them, the phase difference can be 0 or pi, which is not very good news, because our goal is to build a network which will have all sorts of frequencies, all sorts of phases, because I want to model the whole brain dynamics. But already here it becomes so restrictive, you have only two possibilities. So, can you have two oscillators with any arbitrary phase difference? That is the objective. Okay. So, for that it turns out that if you make the coupling strength a complex number, not a real number like this, then you can get arbitrary phase difference. So, take for example, a coupling strength where W12 is equal to this and W21 is this, and they are complex conjugates, right. So, symmetry in complex domain is like, in terms of conjugation, right. So, it is so if you have n oscillators, it becomes a Hermitian matrix. So, if you do that, what happens is you can easily show using simple algebra.
So here we are using the formula as A for I Z for Z.
Yeah.
In the last one, we have the real of Z2 and real of Z1. That's the
Sorry?
in the last one.
Yeah, we are started with real values and show that it is restrictive, but moment you allow complex coupling,
that's what we're capturing in the A for I.
yeah. So, when the coupling is real numbers, because normally you assume they are real, right, you have only restricted possibilities. When you assume the coupling is, then allow them to be complex, then you can show that this angle of the complex number becomes equal to the phase difference. So, you can produce whatever phase difference you want in the two oscillations. So, why am I doing all this? I want to construct general trainable oscillator networks and pose it as a model of brain dynamics. Because we want to model the whole brain, right, and we want to model all this alpha, beta, gamma, all these waves and all that. So, we are building the building blocks for that. Okay. So, now you take two oscillators with a coupling strength like this, A into e power I phi is this, and then you see that the phase difference goes to pi by 4, because the phi is pi by 4. So, you can make it general, you can make any phase difference you want. Okay. That is still not general enough, because in this case the two oscillators have the same frequency, this and this have the same frequency. So, you can get different phase differences, but that is not good enough. I want to have even phase frequencies to be different. How do you do that? So, it turns out that if the frequencies are different but close, they are different but close, then there is a way to make the network behave. I will explain what behave means in a minute. So, if frequencies are different, and if you increase the coupling strength, keep on increasing coupling strength, something interesting happens. So, epsilon is the coupling strength, it is the x axis. The frequencies are 2 and 2.2, right, different but close, right. When the coupling strength epsilon is 0, then this oscillator goes on at 2.2, this oscillator goes on at 2. There is no question of phase difference, right, they keep on doing their own thing. Now, increase the coupling strength. Once it crosses a threshold value of something like 0.2, both oscillators are forced to come together to a compromise and oscillate at some intermediate frequency, which turns out to be something like 2.1, and after that they will have a constant phase difference, that is not 0. The originally faster oscillator will be leading the slower oscillator. So, now they have come to a compromise frequency, but the originally faster one will lead the slower one, and so there will be some phase difference. Yeah.
Why
is the threshold for both the oscillators same?
Why is it threshold?
Yeah,
What threshold?
the threshold at which they behave like a single oscillator.
No, so as you increase this coupling strength, at one point they become the same. Frequencies come to a common value. Okay, so after that you have a constant phase difference, but the point is in the process I have destroyed the diversity of frequencies. 2.2 and 2.12 was there originally, both became 2.1, which is not good. I want to have, because brain has a whole range of frequencies from 0.1 hertz to like a few hundred hertz. So that's the kind of network I want, with lots of different frequencies and phase differences and all that. So how do you construct that? Okay, so now let us take a more general case, right? So this is not very good. Let's take a more general case. I'll have two oscillators, different frequencies, omega 1, arbitrarily different, not close, right? Omega 1, omega 2. I couple them. Then what happens? So how many of you have seen this picture? It's called Arnold tongues, map of Arnold tongues. Okay, let me explain this. So x-axis is the frequency ratio, omega 1, omega 2. Let us say omega 1 is some variable thing, omega 2 is 1, because only ratio matters. And y-axis is the coupling strength, just like the previous case of epsilon. Here y-axis is epsilon, which is coupling strength. Now let us say omega 2 is 1 and omega 1 is like 1.1 or something, slightly different. Now just like before, I have to have sufficiently strong coupling strength to make both come to a common frequency of like 1.05 or something, and after that they'll fire in sync. That is called synchronization. Same thing if it is instead of 1.1, if it is 0.9. Again, you to force it to come to some 0.95 or something, you have to have a sufficiently strong coupling strength. So there is a whole band way which tells you how I can make two different frequencies, force them to come together by giving a sufficiently strong coupling. So that's what this yellow band is telling you. Now take something which is not exactly close to each other. Omega 1 omega 2 ratio is not close to 1, but close to 1.5. or 2 or some simple integral ratio, suppose close to 3.2, let us say 1.5. Then if suppose the ratio is actually 1.6, then again I have to have a sufficiently strong coupling strength to force it to come to 1.5, which is a simple integral ratio. And then you do not talk about synchronization, but you talk about entrainment. That means one will be going at 3, one will be going at 2, and they keep beating like that. So that is called entrainment. And so instead of 1.6, they come to 1.5, that is a closer integral ratio, and that happens at certain coupling strength. And now you can imagine the same thing happening at various integral ratios, but since integral ratio the rational numbers are densely distributed over the real line, this map will be looking very complicated. Okay, so thing is, even with two oscillators with arbitrarily different frequencies, the whole problem of making them oscillate in a kind of a predictable fashion is such a painful problem. That is what this map tells you. So now what do we do? So then we made an interesting assumption, which is don't try to bring them to some any integral ratio or anything, because when the frequencies are different, you can't have constant phase difference. The only thing that you can meaningfully ask for is perhaps the constant normalized phase difference. So what is that? So instead of looking at theta 1 minus theta 2, look at theta 1 by omega 1 minus theta 2 by omega 2. So you normalize each phase by its own frequency, then look at the difference and see if you can make that difference equal to some desired constant. Can you do that? That itself, that could be a good thing to do. So how do you do that? So here we use a trick. So the previous one of using complex weights, I thought we were like very innovative, it's something new that we discovered, but then we found that Izikevich in his book, he derived it already. But this idea of power coupling is not there. This is something new that we have come up with. What is this power coupling? So intuitively the idea is, suppose I have a frequency oscillator here of omega 2, it is getting two inputs from two different oscillators at omega 1 and omega 3. Now in the connection, this frequency gets instantaneously converted into this frequency, and that is what is heard by omega 2. Okay. So similarly from omega 3 at connection some magic happens, and this frequency is magical transformed into this frequency, that is what is heard. So you see, to give an analogy, you see, let us say you go to Japan or something, I assume you do not know Japanese, but you have all these apps now, you say nee eppadi irukku, whatever, right, something in Tamil or something, and translates and says it in Japanese in real time. So, something like this is going on in the frequency domain. Okay, so how does it work? So, same thing, if I have in this omega 1, omega 2, the two are coupled. At the connection, what we should happen is this omega 1 should become equal to omega 2 instantaneously, and that is what is heard by this oscillator. So, there is never any problem of entrainment or anything, because all the inputs coming into a given oscillator are in its own frequency. So, there is no problem of entrainment or all this misbehavior you see in Arnold tongues and so on. How do you achieve this? Answer is very simple, right. How do you convert, this is a sinusoidal oscillation at omega 1, how do you convert this to omega 2? Just raise this to the power this, z1 to the power omega 2 omega 1 will make it, right, which looks trivial, but you see the kind of problems you are getting into. So, this is where engineers rush in, where theoreticians fear to dread, because you are raising a complex number, a complex variable to a real power. It is not even a rational power, it is real power, and you have all these problems of so have you, if you have taken any course on complex analysis, right, I have taken one, and with difficulty I just barely made a decent grade. There is something called Riemann surfaces. Even if you take something called root of z, z power half, which is the easiest problem, right, you have very weird surface you have to draw to determine what is the output of this function. So, now imagine z power gamma or something, where gamma is an arbitrary real number, a positive real number. I mean, what will the surface look like? I have no idea, right. So, that is why I said engineers do not care, we just look for something that works, write programs in Python, MATLAB, it works, it is giving meaningful results, I am done. So, thing is, I believe there will be deep theoretical issues in this operation of z power gamma. We never face any problems in our simulation, so I am just moving on. Okay, but that is for people like you guys or theoreticians here to get into. So, you can easily show that when you have two coupled oscillators like this, and with this kind of operation which we call power coupling, because coupling through by raising the power variable to a power, right. So, in this direction the power is z1 power omega 2 omega 1, this direction the power is z2 power omega 1 by omega 2, and then there is a complex factor, a coefficient, and that also has a special structure, you can easily look at the algebra, and you can easily show that when you do this, I am not talking about phase difference, but normalized phase difference can be made equal to some desired constant. You can easily show using numerical work. So, this is the starting point, right. Now, with this kind of an operation, this kind of a coupling, you can couple all sorts of arbitrary frequencies, oscillators with arbitrary frequencies, and make networks. Now, you can take n oscillators and couple them, and you have stable normalized phase differences. In fact, your Fourier series is actually an example of this, right. Exactly this is what is happening in your Fourier series. This is actually, you can take it as generalization of that. Now, okay, when it comes to biological significance of all, because this is supposed to represent what happens in the brain. So, reviewer said, hey, this is all some random mathematical stuff, there is no connection to brain. No, as we said, no, think about it, because here we are talking about not single neuron, but an ensemble of neurons. If you take single neuron, let us say this neuron operates at generally high frequency, this is at low frequencies. That kind of conversion can take place at the synapse simply by modulating your membrane time constant and your threshold of firing, right. So, similarly, if you take now a bunch of these kinds of neurons with some excited inhibitory balance and all that, another bunch of these kinds of neurons, the average activity of this ensemble will be a high frequency oscillation, the average activity of this will be low frequency oscillation, and the connection now is a whole bundle of synapses, not a single synapse, and this synapse is now behaving like our power coupling. This is how we argued, and kind of the reviewer kind of became silent after some time. That paper is published here. So, now with that we will now start constructing networks. So, now we should talk about training. The networks mean we need to train it, right, to do something. So let us start with training of a single oscillator. What is there to train a single oscillator? Its frequency, which means if I give an oscillator some sinusoid, the oscillator frequency itself is something different, omega naught. Can the oscillator learn to track the input frequency? Frequency tracking is a well known problem in electrical engineering, in signal processing, radar and all that. So, something similar happens here. So, this is the two frequencies originally, and as you keep on presenting the external signal and as you keep training the oscillator, it gets tuned to the input frequency. So, the two frequencies come together. Actually, the oscillator frequency moves towards the input frequency. So, that is a very simple equation. So, this was already proposed by Rigetti et al. In a real oscillator case, we just generalize it to a complex oscillator. So, you can see that in numerical simulation. So, the oscillator's original frequency was 40, the input frequency was 30, and because of training it tends towards the input frequency. Now, let us take a network of such oscillators and make the network learn something. So, you have a network of coupled oscillators, n oscillators coupled by a complex matrix which will be Hermitian because it should be symmetric, and then you take outputs of all the oscillators with some linear weights and sum them up. The output of that should be trained so that this becomes equal to some kind of desired time series. They are very general, nothing to do with brain, it is a very general problem. So, these are the equations, you can train it like this. So, an example, so this is a target signal which you want to network to learn. It has just 3 sinusoids, right, and so in the first stage you train the network only to learn the frequencies in the input signal. Here there are only 3 frequencies. So, initially we take I think some 50 oscillators or something, the frequencies are all widely distributed, but once you present this signal and keep training the frequencies, you see that all the frequencies got clustered in those 3 near those 3 values, omega 1, omega 2, omega 3. So, network is tuning itself to the input frequencies. So, now you train the network with 2 outputs, or you can train it on multiple outputs. So, it learns the signals very well. Then we said let us apply this to some really complicated signal. So, we took EEG signals itself and then trained it. So, you can see that if we have taken 6 channels of EEG signals, it learns it very well both in time domain and frequency domain. Okay, so, you have a general network which is trainable, but we will make it and just like in a neural network, as you increase the number of oscillators, the accuracy of reproduction, right, keeps improving. So, it is like kind of like Fourier series or Fourier transform, or Fourier series is a better example. As you take more and more terms in the expansion, you get more and more accurate fit, right. Only thing is it's meant only for periodic signals and right, but here it is general. The frequency can be anything and it learns from the signal and so on. Now, let us try to make it even more general. So, here we address a very important problem. So, now we are talking about brain dynamics proper. How do you model brain dynamics? So, there is a lab in France in University of Marseille called the Virtual Brain Lab or TVB. Okay. So, so here they use networks of oscillators like this to and train these networks to reproduce brain dynamic data. For example, like what you get from EEG or fMRI or MEG, magnetoencephalogram, things like that. So, when you look at these kinds of models, there is an important dichotomy that you hit very soon, because when you talk about a brain model, it has to do 2 things. The first thing is learn some kind of behavior. You should learn first of all and learn some kind of behavior, that is, if I throw a ball, can it catch, and if I present a picture of a number letter A, can it recognize it or something like that. That is behavior modeling. Then one more thing is to model the internal brain dynamics, right, can it do that? That is what the TVB models can do, right, but they cannot learn behavior, whereas your deep networks can learn behavior, it can recognize patterns and things like that, but they cannot capture brain dynamics. If you look at a convolutional neural network CNN, it will do a very good job of recognizing 1, 2, 3 and all that, but there is no dynamics inside, it does not look anything like brain inside the CNN. So, this is a dichotomy. The TVB models can learn brain dynamics, but cannot do any behavioral stuff, cannot learn anything behavioral, whereas deep networks can learn behavior excellently, right, but they cannot produce brain dynamics. So, is it possible to have both in one model, and that is what we are aiming at, because our networks can learn just like your artificial neural networks. So, so for that we started first looking at more and more complex brain dynamic data, like for example, we got this EEG data from Sujit Vijayan at Virginia Tech. This is EEG data from 64 channels in both waking and sleep and multiple sleep substages and all that. So, we could train the network well, but in this case we have looked at a slight improvement of the network. Instead of having the oscillators and the output, we had a hidden layer, right, and then trained this. These are all complex weights, this is also complex neurons, complex sigmoidal neurons, and the fit becomes much more accurate than before, which is common sense, because what happens in neural networks, if you have a perceptron where there is only input layer, output layer, it is not very accurate, not very powerful, but if you add a hidden layer, then if you arbitrary size hidden layer, then network can learn practically any, a lot of the approximation theorems. Yeah.
What are you using as the learning signal?
Sorry.
What are you using as the learning signal? So you mentioned that.
So the network will just try to reproduce the time series.
Okay, so there is an action that is the
No, it's just a generative model. It's taking a time series and learning to reproduce it. That's all. It's not an input-output problem. So this work actually got published just recently. Then we also looked at data from fMRI. Right, in fMRI, again that's where actually a lot of these TVV models are applied. So here the goal is to people take what is called structural connectivity data. That is, if you look at, here the brain is divided into a bunch of zones or regions of interest. Typically a few hundred such zones are taken, and then there is something called diffusion tensor imaging, where you look at the tract bundle density, right, connecting a pair of an ith zone and jth zone, and that matrix is available. So idea is you plug in this matrix into a network of oscillators, and network should be able to reproduce your brain dynamics. That's how the problem is posed. So we have taken this kind of data and again kind of modified the network a little bit. So you have again here you have the input layer is a bunch of oscillators, and output layer is supposed to produce the fMRI data. There is a hidden layer of sigmoid neurons, but kind of the architecture is slightly specialized, because for each ROI I have one oscillator and it's coupled to a bunch of other oscillators depending upon the DTI information, the structural connectivity information, and then for each of them there is a separate hidden layer connecting to its own output. So we train that again. You see that the fit is so, because fMRI is a very simple signal. I mean, it's a low frequency, very narrow band, low frequency signal. So you can see the both are, you can't even see the difference. So this was also published a couple of years ago. So then there are examples of generative models. Then let's look at a model of self-organizing maps, right? And so there are examples of this kind of oscillatory maps in biology. A great example is the cochlea. In cochlea, there is a place called basilar membrane. So where if you play a sound, right? So if you play for example a pure tone of some frequency, they will produce a local vibration in this kind of a membrane, which is like elongated, like a linear membrane, and so it is doing some kind of a Fourier transform of the input signal. All this happens. This is all rolled up inside the cochlea, but if you stretch it out, it looks like a nice Fourier transform performing structure. Another example is the auditory cortex of mammals, but a lot of work is done on auditory cortices of bats. The bats are very good at navigating by throwing sounds, right, by echolocation. They are not totally blind apparently. We generally say blind as a bat, but apparently they are not totally blind. But they use sounds a lot for for navigation. And this work done by Nobuo Suga, a Japanese researcher. So this is the primary auditory cortex in this is a certain kind of a bat, and here you can see there is a nice map of frequencies along a linear strip of the cortex. So this operates in ultrasound range. This is 100 kilohertz and 10 kilohertz. Between the two, the animal itself transmits around 60 kilohertz, plus or minus a few kilohertz. That is the range in which it transmits, and therefore there is so the lot information is in that small band, because the return signals also come in the small band. And so for example, if it is looking at another moving object, there is a Doppler effect and there is a shift in frequency, and all that happens around the small band. So it has to capture the information in that band. So therefore a lot of area is allotted to that small band around 60 kilohertz, but other areas are not very informative, so it has lesser area allotted. So we constructed, this was my student Deepayan's work. So we constructed a map, 2D array of oscillators, and here the idea is that the rows represent frequency and the columns represent phase differences. So to define phase difference, we felt the need to use some kind of a reference oscillator, and so we could kind of see some analogy between the cortex and thalamus in this kind of arrangement, but anyway that is a slightly fancy interpretation. And so if once you train the network, you see that if you present a pure tone, entire column of oscillators respond to that, and if there is a particular phase in that input signal, a subset of those oscillators will show even higher response. Okay. So, each oscillator in the map, in this 2D map, is representing a frequency and a phase difference. So, this is for one frequency, for two frequencies, and if you give a complex signal, lots of rows will respond to that. Next, we also want to see some hardware implementations of oscillators, because that is, I said, there is a lot of work going on in that area. So, we wanted to model locomotor rhythms, and here we took something called a VO2 memristor, a kind of a nonlinear conductance. If you combine it with a conductance and a capacitor like this produces oscillations, as you can see here. So, we showed that if you use 4 such oscillators coupled by 4 capacitors, and by varying the capacitor values, you can produce different kinds of locomotor rhythms. These are, because quadrupeds have very rich locomotor rhythms. I mean, humans are in that sense not very rich, unless you are a dancer or something. So, you have walking, trotting, pace, gallop, it all depends on the exact phase differences. You can capture the whole variety of them simply by playing with these 4 capacitor values. So, this was published again a couple of years ago. So, now we still haven't shown you the final model, which is input output model of oscillators, where you have hidden layers of oscillators. So, that is finally what I am showing now. We had a lot of trouble making this work, but finally it is working. So, here you have network of oscillators, input and output, and actually it is a hybrid network. Some layers are oscillators, some layers are sigmoid, and all the connections are complex numbers. So, how do you train this? So, we were able to train this. So, some simple examples. So, first example is autoencoder. Input signal, output signal are both the same. How do you train this? So, it works. You can see that it's learnt it well. Then something like integration, which is interesting because there is memory involved. So, it learns it well. We made sure the signal is 0 mean, otherwise you will have a huge build up with time. And amplitude demodulation, interesting signal processing application. So, it learns that. And now more complicated, we are now began to look at data sets from machine learning, and something called action recognition from video. So, here we looked at the oscillator version of convolutional neural networks, oscillatory convolutional neural network, OCNN, and it learns very well. It beats some of the competing models in deep networks. So, video frame prediction. So, you show a video frame in a sequence and it predicts the next frame. So, you see that this is the oscillatory convolutional neural network, this is a convolutional LSTM. This is like a workhorse of RNN and sequence processing networks in machine learning today. This is our oscillatory convolutional network. So, what I want to show is it is not just for brain data and comp neuro applications, even as a artificial machine learning tool it is very powerful. So, our big goal is to, I am very fond of Bazaki's work. He has written this classic on oscillations called Rhythms of the Brain. And so, in fact, he talks about all brain phenomena in terms of oscillations, not spikes, but in terms of oscillations, right? In terms of this happens in theta, this happens in gamma. But here you have some kind of relationship between theta waves and gamma waves, and there's a huge amount of literature on those lines. A lot of empirical stuff and a lot of hand waving and so on. No grand theoretical framework. The idea is to use this kind of models to produce that. So, we are on the way to do that, especially in the area of hippocampus and spatial navigation. You have all these concepts of theta, theta precision and so on and so forth. We seem to be getting a very good, very logical interpretation of some of those phenomena. Maybe that is for another talk, because still work in progress. The idea is to create a whole comprehensive integral oscillator theory of the brain using these kinds of general networks. So, for navigation, for attention, for motor function, autonomic control, pathology. Because oscillations go haywire in pathology, in brain disorders. The idea is here we are looking at brain as some kind of a oscillatory medium. You can draw analogies between radio communications. The radio communication, for example, this is your bandwidth. You are forced to operate within this bandwidth. Why is that? Because if you go less than 3 hertz, wavelength becomes much bigger than Earth's diameter, so your signal won't come back. Right? If it goes more than like 3,000 gigahertz and all, it will be too expensive to transmit because there is too much loss. So, you are forced to operate within that. So, similarly in brain's medium, instead of thinking of brain's computations as happening as driven by neurons with communicating by spikes and all that, think of it as a nonlinear medium, a continuum in which waves are propagating in the 3D volume, which is true. That is also an equally valid way of looking at brain's computations. And then that medium, just like the Earth's atmospheric medium, that medium can only support perhaps frequencies from 0.1 hertz to a few hundred hertz, right. More than that, it will just filter it out. So, which means now the question is, just like in radio you have allocation, you have 3G, 4G, 5G, there is allocation problem, right. Here allocation problem is, in which frequency band will you put vision data, in which frequency band will you transmit auditory information or motor or mood information. Okay, memories, how do you encode memories in using oscillations? Okay, so this is the problem. So, I mean, I think this kind of a framework will help you negotiate these questions in a logical fashion, but I mean, that's future work. This work is at least 6-7 years old. I mean, we've been doing this for 6-7 years or even more. But now I think there's a lot of exciting stuff to be done. So, if you want to do projects or internships or PhDs, and you are most welcome, you can have like a whole army of PhDs, working on, to work out this whole scheme. It will take a lot of people. So, let me stop there and thank you.
Questions?
Yeah.
Like you talked about the architecture, like you mentioned the layer of nodes and the oscillators. So like in, yeah. So like how do you got into architecture, because it's very hit and trial thing, like how many years you will take?
That's it depends on the problem.
So it's a hit and trial, or you found out some process, okay, like this is standard way?
No, whatever we do in deep networks is the same thing here.
The same.
Yeah.
It's hit and trial.
No, just like deep network, just that we have oscillators. But what is nice about theoretically is in a deep network, for example, there is a concept of tuning, because that's relevant to neuroscience. We talk about single neuron tuning to orientation, all these things. When you talk about oscillators, tuning will be in terms of amplitude, frequency, and phase. Okay, so now the frequency tuning and phase tuning can be related to phase precision and things like that. So, very naturally go towards some of these biologically observed phenomena. If you look at this broader definition of tuning of oscillators, this is what I am saying. If you have a good oscillator theory, first work out the theory and apply it to biology, you will find very elegant explanations. So, some of these weird phenomena like phase precision and velocity dependence of neurons, and because in hippocampus literature especially, it's like a zoo of cells. You have time cells, place cells, grid cells, corner cells, you just make up some random stuff. There is no grand theory. It's not like quarks, which are only so many quarks are possible, and it's not like that. Anything, you just find some random stuff and give a name to it. Whereas with oscillators, I think it can be put in a proper theoretical framework.
So, sorry.
Sir, on the last slide, there is mention about brain disorders. So, has using oscillatory models, has any of the neurodevelopmental disorders been looked upon, like autism or ADHD? Has it been?
Not neurodevelopmental, but neurodegenerative, I can give examples. Take for example Parkinson's, right? Take one of the key observations of pathology, right, in Parkinson's is subthalamic nucleus oscillations, synchronous oscillations in the beta band. In fact, synchronous oscillations in the brain is a hallmark of pathology in many cases. Another classic example is epilepsy. So, you have high intensity, high amplitude oscillations, but low information, low entropic content. So, that is a sign of pathology. You are not even conscious. There is a lot of activity going on, but you are not even conscious. So, in fact, it will be very interesting to talk about build a dynamical theory of brain disorders. You will see this pattern in many problems.
So the final slide that you showed, yeah. So no, this one, yeah.
Yeah.
So,
I skipped that.
Yeah, I know. So I remember talking to you a couple of times about this gradient. So what is the idea that you're?
So gradient we explored this in the heart context, because, but the idea here is suppose you took a feed forward network, okay, sensory input, motor output, could be some reaching problem or something. You train it, right? Then in the training, since you are these oscillators, we also train the oscillator frequencies. Okay, initially they are all random, but after the training, will the network develop a gradient? Why do we expect that? Because if you look at the real brain, people have found some kind of a gradient going in this direction, anterior posterior direction. So, will you see a corresponding gradient here emerging simply out of training without putting it by hand? Then it is a good model, I mean it is a good approach to oscillations.
What are the parameters that you train?
Frequency and the weights.
The weight,
Yeah.
frequency weights.
Yeah.
But Srinivas, like for example, even if you look at the brain state, they are characterized by different frequencies.
Yeah.
For example,
Yeah.
delta.
Yeah.
Is this frequency gradient there even no matter what is the overall frequency of the waves?
No, I have to look at that exactly what gradient, what are the numbers.
Right.
Look at it.
Because there's also a temporal change
Yes,
of the frequency.
yes,
Right?
yes.
So you're saying that there's also spatial.
Yeah, there is spatial organization. Yeah, the different systems operate in certain prominently in some frequencies, like theta, gamma. But I'll tell you, the literature is very sloppy. You cannot say it too loudly. I'm talking about top journals in neurobiology. For example, there's a very grand idea. I thought I liked the idea. The idea of a so in hippocampus, the two pathways, right? The entorhinal cortex to CA1 and there is a longer route. It's kind of a direct and indirect pathways. There are two complementary pathways. The idea is that for high frequency gamma, one pathway is chosen, low frequency gamma, another pathway is chosen. Some kind of story. Okay, I liked the idea, and then I went and talked to that proposer of that theory in UT Austin, because we think on the similar lines for basal ganglia. I said, oh, that's why I'm very excited. I want to learn more about it. She said, we retracted. We don't believe in the idea anymore. No, it's things are very it's loose soil. The field is on. I mean, talk about Nobel laureates involved in such papers. It's just going in circles, and that's what is published. So, in that, if there's a grand theoretical framework, puts it on a rock foundation, it will be really beautiful. It will save a lot of money. I mean.
Okay, so
Yeah. Thank you. Thanks a lot, and
thanks, Srinivas.
thank you.